All right, so continuing on, just our last section here, still on Newton's second law. So Newton's second law applies to his first law by stating that in a given situation, the mass that's multiplied by the acceleration will give that net force applied. And so I've mentioned this in all of the examples that we've done so far and have tried to really emphasize that point in the difference between the net force and the normal force. So remember, the normal force is perpendicular to a surface when two objects are in contact, whereas a net force is the overall force in a given plane or a given direction. So we're going to start to take a look at some given planes and take a look what the net force is. So the net force can actually be used in a couple of different scenarios. So if I have a box sitting on a plane, I have four forces right away that are acting on it. I have a force applied in the horizontal plane, okay, going right across the horizontal plane. I have a force applied, and I have a force of friction. That means that the net force will be the addition or summation of both of those forces. So the net force in the horizontal direction would just be force applied plus force of friction. That would tell me the overall unbalanced force in the horizontal plane. If I want to know the overall unbalanced force in the vertical plane, well then the net force in the vertical plane would be the force of gravity plus the normal force when two objects are in contact. So I can take a look at this and kind of come up with expressions for this. Right? The net force horizontally is force applied plus force of friction, and the net force vertically is force of gravity plus the normal force. And so if I'm looking at a problem and that problem needs me to analyze the horizontal motion of an object in order to calculate its acceleration or its force, then I now have two different equations that could solve for net force, because net force could equal mass times acceleration, or net force could equal the force applied plus the force of friction in a given plane or a given line. So we now have three separate parts, but really we only would connect them with two, whether we deal, depending on which plane we're dealing in. And so it's going to be helpful for us, obviously, to see an example and see this played out. So what would happen to the net force if the force applied were causing the box to move at a constant speed? And so if we think about this key term from before here, okay, what would happen to the net force if the force being applied were causing the box to move at a constant speed? So if I'm applying a force to an object and it's traveling at constant speed, if I go back up to my equation, remember, constant speed from before means that there's no acceleration. If there's no acceleration, then there's no net force. So if I'm applying a force causing a box to move at constant speed, that means that the force of friction must be exactly the same as the applied force, just in the opposite direction. So if I'm applying 10 newtons worth of force moving forward, that must mean that I must have 10 newtons worth of force moving against me in order for it to move at a constant speed. So let's see this played out. So as an example, a person pushes a crate weighing 5 kilograms with a force of 10 newtons, and if the frictional force between the crate and the ground is 2 newtons, with what acceleration is the crate moving? So picture, and we can kind of sketch out what this looks like, and I'm no artist by any means, but picture that somebody is pushing on a crate, okay, and they're pushing that object moving forward. Okay, so they're pushing this crate. We know the crate weighs, the mass of the crate weighs 5 kilograms, and we know that they have a force being pushed of 10 newtons. Now this is a complete horizontal problem. It doesn't mention anything here about lifting or being vertical or anything like that. So I have this equation now from the last one that we can kind of start to use here, where we say the net force, which is really going horizontally in this case, is equal to a force applied plus a force of friction or force resisting it. So force of friction in this case. So weighs 5 kilograms, they're pushing it, so they're applying a force of 10 newtons moving forward. It says the frictional force in here between them going backward, frictional force is 2 newtons traveling backward. And so if I take a look at my net force equation, remember that opposite, the sign will be negative if I have something moving backward. So I have 10 newtons moving forward plus 2 newtons slowing me down, 2 newtons moving backward. That means that the net force in this scenario is just going to be 8 newtons moving forward. Take a look just for significant digits. Remember, when you add, you go by place value. Both numbers are in the tenths place, which means that I've got 2 digits there. After that, the question is saying with what acceleration is the crate moving. So I have a problem, or have an equation with this, where the net force can equal the mass times the acceleration. So my acceleration, just rearranged, would just be the net force over top of the mass. Acceleration is equal to, the net force of this is 8 newtons, and the mass of the crate is 5 kilograms. And so I can see from that that the acceleration for this, 8 divided by 5, just gives me 1.6 meters per second squared, and that crate is moving forward. So hopefully we can see how you can use a horizontal force, whether it be applied force, having a frictional force. I really have 2 different net force equations now, and lots of different things that I could try to calculate. So while you're working on some of the problems for this, what I would really encourage that you do is to draw pictures and try to analyze them. And then make a givens list, see if you can solve. So remember that all forces behave the same under Newton's second law. They all have some kind of connection that we can use vector lines for to draw them out. So all of these so far have been objects in contact, but what if we have an object that's in free fall? In that case, the net force, if an object is in free fall, really what we have here is a force due to gravity pulling it down. So the net force really here is the force of gravity. It's still a force. It still is equal to mass times acceleration. But really, what is acceleration when an object is in free fall? And hopefully your answer for that is that really F net would just equal mg in free fall. So if an object is falling, then I can figure out the net force because I can take the mass and multiply it by the gravity. Now, in reality, when we start to calculate this, you have air resistance that's slowing things down. Where we're just starting out, unless a question specifically mentions what the force of the air resistance would be, we tend to neglect air resistance and just assume that the drop isn't a large enough distance where an object in free fall would have a drastic amount that would reduce it. So just where you're just starting, we're not going to worry about objects resisting or air resistance too much. We're just going to concern ourselves with objects in free fall. So in this case, the force of gravity, you may see it called in some problems the weight. And so weight just has a capital W with it, but it's the exact same thing as the force of gravity, okay, for our purposes. So you're now ready for our next worksheet on Newton's second law. It just goes through and practices a few different concepts and different parts. So let me know if you have any questions.